Okay, let's start. Let's start. Okay, so we talk about Ito's formula, right? This is the basics of stochastic differential equations. So it's a totally different, not different, but separate subject. So all we doing before, right, in this whole course, so it's kind of except for the Brownian motion part, it's all like discrete, right? A discrete probability. But you know, there's a whole branch of mathematics, right, which we call calculus or analysis, right? So it's more modern way to call analysis, but analysis is nothing, right? It's just a calculus, right? Maybe a modern version of calculus. There are a lot of things. I mean, but the word is definitely discrete, right? But sometimes it's more convenient to using continuous approach, right? So if you talk to some people doing physics, right? So they might argue the word is discrete, but there are a lot of continuous intuition, right? Like the fluids, right? But there are a lot of continuous things, right? So that's why people use calculus, right? So this function, continuous functions, but you really say, right, they're only, right, so the atom point of view, right, is a discrete, but that's not really, I mean, but then doesn't make, it makes sense, but it's not useful, right? So calculus is one of the useful tools, right? It's a big jump, right, in mathematics. We want to study probability using calculus, right? So this is called Ito's calculus. So when people study, right, stochastic analysis, there are different tools, but the Ito's formulation, right, Ito's way becomes more popular, right? So now it's like dominant one. So people usually just use Ito's formula. So Ito's original paper, like, is most cited one in the history of mathematics. So you can see, right, that's why, so that's why it's very important, right? It's get a lot of applications, right? People study financial engineering, they know this very well. There's another type of defined integral, right? So it's called, so let me find the name. Usually I didn't say this name probably. It's called, so Straight-Norwich. So this is another way. This is a Russian guy. This is a Japanese guy. So this happens in last century, right? Last 50s or 60s. But at that time, right, they didn't communicate that much, right, between like, Russia and the Western world, right? So this Straight-Norwich way of define stochastic integral is a little bit different with respect to comparing to Ito's formula, but in essence, right? So they are equivalent, right? But Ito's calculus or Ito's formulation becomes more popular nowadays, right? So we just talk about Ito's calculus. But if you study, right, if you study like stochastic partial differential equation, right, SPD. So in some settings, it's more useful, right, to use Straight-Norwich calculus. Right? So, but that's totally different, right? More usually we use this formula. So let's just state the first version, right? We will state 3 versions of Ito's formula. So here, let's just see the first version. So the first version is the following. Okay, let's say we have, we know the Brownian motion very well, right? So now we have a C function, right? So C2 function means you take derivative F, take second order derivative, they are all continuous, right? So it's C0. Then we can write, so then we can write the following formula. the following formula. Let's open one more page so I can write that. Right? So what is this formula, right? What was this formula? So this is a very the first formula, but if you understand, so you can do others in the similar way. What's this formula? Right. BS ds plus 1/2 from 0 to t f prime bs ds. Okay. So so f here is just a function which is C2, right? So it's called twice differentiable, twice continuously differentiable. So it means you take second order derivative and the first order derivative, second order derivative are both continuous. Right, so this is called, so then we can just write, right? So we can just write the difference. So you can think this is a difference. So this become equals, right? So if, right, so we know the following pretty well, right? So let's say if it's not BT, right, this is Brownian motion, right? If we just have a continuous path, X, there's no randomness at all. If it just has a continuous path, if we just have a continuous path, what can we do? Right? If we just have a continuous path, right? So then we just have the following. We just have the following. Yeah, so I think I'm wrong here, right? So they didn't tell me. So if you have a continuous path xt, right? So this is what we have, right? By calculus, right? So this is just a Newton's rule, right? Fundamental theory of calculus, right? It's the differential integral way. So what does it really means, right? So this really means, right? If you take derivative xt with respect to time, right? So if we take derivative with respect to time, right? So what do we have, right? So then we use chain rule, right? So this is xt. So then this is xt dot, right? So this is a time derivative, right? And these two ways are equivalent, right? Because this is a integral way, and this is differential point of view, right? So just two equivalent, right? So if xt, right, if xt is deterministic and xt is differentiable, right, is a differentiable curve, right? Then we have is just the first term, right? Is just the first term, up to the first term, right? So, but you can see we have one extra term, right? We have one extra. So this term comes from stochasticity. Stochasticity. Okay, so this comes from stochastic property. And so this part, right, is the calculus, right? Fundamental theory of calculus, right? And this term is Ito's correction. Right? So we will just prove that, right? You can see, right? So if xt, right, if xt is a differentiable, right, if xt is a differentiable curve, actually there's no this term, right? Then the last term is equals to 0, right? But we know, right, from the very first lectures, so bt is not differentiable, right? Is not C1, right? So it's not C1. So this term actually is there, right? So this term, right, the last term. So if you just look at this term, it's more clear. But I can tell you, right, this comes from the second order term. in Taylor expansion. Okay. So usually, right, so before we go to rigorous development, right, you can think in the following way, right? This is the first Ito formula. So it's like, right? First we have Brownian motion, and we have F, which is C2, right? So F depends on the space variable, right? F equals to Fx, only depends on space variable. So now if we take the differentiation, right, of Bt, what do we do, right? What do we do? So the first one, right, is a Euler first order term, right? It's just differentiation, right? If there's no stochastic, right, that's it. But we have a stochastic term, stochasticity, right? So we expand up to the second order term. We expand second order term. And this term, you can think this is as Taylor expansion to second order term. And so intuitively, right, so dt is just a dt, right? So that's why we just write bt dbt plus 1/2 f prime dt. Right? Okay, but we have this formula, right? What this formula really means, right, is just our previous integral formula, right? So when we write the differential formula, right, it always corresponds to an integral formula, right? So this is a different way. And this corresponds to the integral way, right? The integral way, representing this, right? I, right? So I, okay. So as I said, right, so this is equivalent to fbt minus fb0, right, equals to integral from 0 to t fbs db plus half from 0 to t bs ds. Right? So these two are equivalent. Okay, so so we basically want to show, right, so why this two, right, why this relation makes sense. So we just want to show how to get the integral form, right, how to make this, so make sense of the integrals. So we want to make sense of these integrals, right? So this is not the Euler integral, right? In particular, the term is not the Euler integral, right? So what dBs, right? We don't know, right? Because Bs is not BV, right? So Brownian motion is not BV. So it's not a bounded variation, but it has a bounded quadratic variation, right? So this is exercise. But this term we know very well, right? This term we know very well, right? It's just a Euro-Riemann integral, right? But this term we don't know, right? We should make sense of the first integral, right? Okay. Let's go back. Let's go back. Yeah, this is the basically what we want to show, right? This is the theory, right? This is the theory. Intuitively, right, you can just seek dBt informal calculation. Informal calculation. This is a rule. Right, informal calculation, right? If we have a 1D Brownian motion, right? So let's say this is a 1D Brownian motion. If you have terms like this, right, you get dt, right? Later, if for multi-dimensional Brownian motion, di, right, dBtj, right, the independent, right? So bti are Brownian motion in I dimension, right, in I axis. So btj are Brownian motion in j's axis. So I and j are different, right? So then here we could I dt. It's for formal calculation. But here, right, if we just want to prove this theory, right, there's one thing we need to make sense, right, is this term, right? It's just the integral, right? What does this integral means, right? So this is just the Ito integral. Ito's integral, right? We should make sense of the Ito's integral. Right? So this is what we do in the following. Okay. So let's see. Okay, like how to do rigorously, right? As I said, right, we just using Taylor extension to second order and checking all the details, right? So basically, we take a Riemann sum, right? And we take the Riemann sum over partition, right? So for instance, this is a partition P, right? So we have a Riemann sum over this partition P. Then we make this partition of the time interval to be smaller and smaller, right? So that means the mesh is finer and finer, right? So we let this to be finer and finer. So then we expect the Riemann sum will converge to an integral, right? Converge to a random variable, and this random variable will be our integral, right? Ito integral. Okay, so how to do that, right? So we fix time t, right? So this is initial time, this is time t, right? We fix time t. So we define, so here we choose a very specific partition P. So here, I mean, you don't need to do exactly like the following way, but the following way is kind of dyadic decomposition of interval from 0 to t, right? So what does this decomposition means, right? We have the interval from 0 to t, and we divide this interval into 2n subintervals, right? They have equal lengths, so they have equal lengths. Okay, so so we just use the Taylor expansion. I mean, Taylor expansion, right, is kind of widely used, but it really should call the Newton's expansion. But that's not very important. So what is Taylor expansion? Right, so let's say we express the function value and point B according to FA, derivative on FA, and this is the remainder, right, the remainder term. Right. So what does this mean, right? To evaluate the function increment, right? So this is the function increment, right? We can approximate using the linear function. This is a linear function, right? The linear function slope is given by the derivative, right? You know this very well, right? And this is the correction term. And the correction term is given by the second order derivative times the 1/2 b minus s squared. And here C, right, is between A and B. Right? It's just anyway, or any point. It's just a one point in A and B, but we don't know where is this point is, right? This is the expansion with second order remainder term. So if we just use this, right, and using the partition, right, using this partition P, right, so we can express the FBT minus FB0, right? So FBT minus FB0, right, is just the increment over those subintervals, right? Over these subintervals, right? So we sum up. So then on each subintervals, we using second order, right? We using Taylor expansion, right? We use Taylor approximation, right? Using Taylor, right? So we get first term, right? This is first term, and also the second order term, right? So it's not magical at all, right? So we expect the first order term, right? This in, right? This is this is 2n. So we actually expect in goes to integral from 0 to t f prime bs dbs, right? This makes sense, right? This is dbs, right? This is the derivative and bti, right? Expect this first sum will goes to the first integral, right? This is Ito integral. So why this is Ito integral, right? Because we choosing the beginning point, right? This is the subpartition, right? Ti n, right? This is Ti n. plus tin. So here is I plus 1. In Ito's integral, right, in the Riemann sum, we take the point, the function value in this point, right? So in this way, we get Ito's integral. So if you choose the point in the, right? So let's say, right? So if this term, right, you choose the Riemann in the following way, FB tin plus ti plus 1n over 2. So then you times the increment of Brownian motion. So if you do the sum like this, okay, so then there has a limit as well, right? Under some proper assumptions. So you have a limit as well, but here is not Ito's integral, right? It's this integral, right? So this way you get just the Stoyanov integral. Okay. So but here we just choosing the beginning point, right? The beginning point, right? You may argue as well, right? We can choose the last point, right? We can choose the last point, right? In that way, you get a backwards type integral, right? There are also something like that, right? Probably you know this, right? In Riemann integral, right? When you study advanced calculus, like some course like that, so the choice of the time really doesn't matter as long as the function is integrable, is Riemann integral, right? But here it's different, right? So here the meritability, right, adaptability actually matters, right? So the way you choose this point, or this point, they are different, right? They're different. Okay, so here we just choose the beginning point, right? BTI, right? So this is the first order term, right? We will show as n goes to infinity, right? As partition goes to finer and finer, we will converge to this Ito's integral, right? So the last term, right, is the second order expansion of the Taylor approximation, right? The second order term. And this term, right, let's say this is in, right? This in actually will just convert to 1 from 0 to t f prime bs ds, right? So we will have the approximation like that, right? So the following, in the following, check the two approximation, right? We just check the following two convergence, right? As n goes to infinity, right? As n goes to infinity, right? So basically, it's just right. So this is all right. This is true for all integral theory, right? So it's like Riemann sum. Riemann sum converges to integral, right? It's slightly different in the big integral, but as I told you in last semester, right? So Riemann integral, right? Riemann sum. In some sense, is more useful than the big integral. But that's another problem, right? So let's ignore that first, right? So as I said, we will prove the following, right? First approximation, Riemann sum will converge to this, right? The second order term will converge to the last term, right? So here we say in probability, but so if a sequence converge in probability, and we refine the sequence, right? We have a subsequence, we can improve it to almost surely convergence. Okay, and from the estimate, so we actually first get this converge in L2 sense. So this is converge actually is in L2 sense. So basically you can think here, the Riemann sum converges to integral, right, in all sense, right, in probability sense. Almost with probability 1 sense, right? Almost surely or in L2. But you need to check this later. But and at this moment, let's just say wiggly convergence, right? So not let's not specify that, right? But as I told you, right? So this can be made to be strong convergence, right? Almost surely convergence. Okay. So let's do the first part, right? Let's do the first part, right? We want to show the convergence of this to I1, right, the integral. f prime bs ds to show that, right? But this one actually is not known yet, right? So we are kind of define this, right? We are kind in the process of defining the Ito integral. This one is not there, right? To have the existence of the integral, right? We should starting from Riemann sum, right? We kind of should get IM1, right? Is kind of compact, right? This is compact or is quasi sequence. So here, right? So what we are going to show is a very straightforward, is a quasi sequence. So in L2, so if this quasi sequence in L2 and this L2 is a complete space, right? L2 is complete. So if you have a quasi sequence in L2, right? So then, so IM1 will converge, right? Converge in L2. So then we'll just converge to a random variable, right? So I is a random variable in L2. So then just identify this limit as the integral. And you can show, so this limit I, right, doesn't depend on your partition, right? So this I is there, right? We have existence and uniqueness. So I, the integral is defined, right, in this way, right? Okay. This is standard procedure, right, in analysis, right? So in define integral, right? So when you study advanced calculus, right, Riemann sum, right, you follow this idea, right? But in there, right? So the space is just in real numbers, right? It's not in L2 space, right? So when you define Riemann integral, right? So here is not L2, right? It's just a real number, right? But here is L2 space for random variables, right? So L2, what L2 means, right? So it means we have a random variable. So this random variable finite two moments. Okay. How do we show? So then the following is just to show this sequence is a co-sequence, right? So how to show that? So I found the development in textbook can be a little bit misleading, but I will just, you can check the technical details. But since they want to using all those notations with explanation, right? Sometimes we just starting from your intuition, right? It can be more fast to get the result. Okay, so let's just using the way in the textbook, right? So what is idea? So okay, let's first, right? We divide this into two M pieces, right? Two M pieces evenly, right? So then, right, use a number n, right? If n bigger than m, what does this mean, right? So if n, so then we just keep dividing this, right? Keep dividing these small intervals, right, to even pieces, right? So we want to compare, right? We want to compare IM1 and IN1, right? So this one is a Riemann sum, right? But this is a Riemann sum over more finer pieces, right? So Riemann sum over finer pieces, and we want to estimate the difference, right? We want to estimate the difference of this. So what's this? I don't want to let you check all those things, right? It's very easy to check. So what's the idea, right? What's the idea is the following, right? So I just write a very easy way, right? So let's say this is I over 2m. So how to say that? This is I over 2m, I over 2m. Right, this is a consecutive dividing points in the partition 2m, right? So then if you keep dividing this, right, you get more dividing points, right? Let's say this is new dividing point, right? So then when you take the difference of IM1 and IN1, right? So for IN1 is the same, right? It's the same. But for IM1, right? Let's say for these pieces, right? So previously, right, you always use this point. So, but now you are doing final sum, right? You compute this part, and this part, right? So then for the xg over 2n over t, right? So for, let's say this is g over 2n over t, right? You should all use the value and to this point, right? So given j, you should be able to compute this I, right? So I is kind of coordinate in 2m system, right? J is the coordinate in 2n system, right? So then this is the change of coordinate, right? This is just the change of coordinate. So anyway, so we have the following formula, right? So we can just take the difference, right? So this is like for n in j, right, in this interval, right, this point to represent this value, right, this value. We just use the atom point. So you can check this easily, okay? Anyway, right, let's call this hg, right? Let's call this kgn, right? So then what's the difference, right? This is im minus in, right, equals to oj, right, oj from 0 to 2n minus 1, right, we take the sum, right? So this is the difference of two Riemann sum. So if this is a Cauchy sequence, right, if this is a Cauchy sequence, what does this mean, right? So Cauchy sequence really means the following. Take expectation. This should goes to 0 as m, n goes to infinite. Okay, so both of them goes to infinite, right? It's definition of a Cauchy sequence. So it's easy to take that. So why, right? We just complete square, right? We use this formula, complete square, right? So then we keep tracking the diagonal term. So this is diagonal term, right? So this is diagonal term, and this is off diagonal term. If you do the x, so if you do the exercise, this is a homework problem, right? So it's the techniques is exactly the same, right? So we expanding, we complete the square, right? We double indices, right? We double indices, right? Previously it's j, so now we double indices, right? So so instead of square, we just consider, right, k. So the same term, right? We can square, right? So this is we do. As I told you, right? So also, right? This is also similar, right? So when we show L2 weak law of large number, so it's the same techniques, right? So this is everywhere, right? When you show like a ergodic theory mixing property, people also use this, right? That is basic technique. So when we have a square, we square, right? So not just the Euro way or complete square. Right? We using we introduce double indices. Okay, so what does this mean? Let's say we have A1 B1, right? Square, right? So now, right, we are not doing just A1 plus B1, right? So now it's A1 plus, I mean, it's example, but here maybe we use a different way, right? It's the computer, right? It's the AI, right? Square, right? So the Euro way, right? It's just a computer square, right? AI, but we're using two indices, right? J, A, J, right? So then, right? So we can right? We keep tracking all the diagonal term, right? So this is AI square, and also all the off diagonal term, right? I not equals to J, AI, AJ. Okay, so these are the techniques we use here. But very surprising is the following, right? So let's say G less than K, right? By symmetry, you can just compute the terms G less than K. And since K is bigger, right? So this is K, right? This is TK plus 1. So this is G plus 1, DJ, right? So DJ is here, right? TK is here, right? And you can check, right, all these things, right, only on this part. right? So all these random variables only depends on information up to time tk. And then this random variable is independent of the previous one, right? So if you take expectation, and this expectation gives you 0, right? So expectation of the increment of this part, you have 0, right? So this tells us when you're taking expression, there's only the diagonal term has contribution, right? Only diagonal term has contribution. So that's why we get the following, right? We keep tracking, we only keep the diagonal term. Then so by independence as well, right? So if you just keep tracking diagonal term, right? This and this are independent, right? Why? Because this we take in the beginning point, right? Beginning point is independent increment, right? From motion, Markov property. So this part is just uh, the variance, right? Just the variance, and we sum up. Okay. So if we sum up over J, right? So this part actually, if we just sum over J 2 minus n t, so this you just get a t, right? You just get t. And we need to show, we need to have uniform bound on this random variable, right? So if we have a uniform bound on this random variable, and we want to show this can be 0 as n goes to infinity and m goes to infinity, then we are done, right? So this is easy to show. So why? Because, right, so we can control this. We can control this, right? This hj and minus kj. So what does this mean, right? So this basically means, so this is, so this is basically means the maximal increment in this time. So this, why? Because we comparing, so because HGM, right, as I choose, right, is from this part. KGN is in some finer point, right? KGN probably here, right? This is a KGN, right? G over 2NT, right? HGM is at this point, right? And KGN is a value for Brownian motion value and this. Okay, so this is F, right? I over 2MT. So this is B. Let's call this TI. Let's call this TJ, right? This should be M, N, right? TIM minus FB TJN. Okay. So we can control these two terms. We can control these two terms. So is prime, right? So by the second order derivative, f prime, the upper bound of f double prime. So then this is just the maximal value of Brownian motion, but these two times S and R are very close. So these are very close. This is less than this, right? What's that, right? So the increment is just 1, 2 over t. So this is the time difference, right? So S and R should be and bigger and minus 2m minus m 2 minus m times t. Right? This is the estimate, right? You can, right? So this definitely is true, right? If you send m goes 0, right? You send m goes to 0, right? So what's this, right? So this goes to 0, and this goes to 0 as well, right? So we just using full estimate. So we actually can get explicit estimate, right? So we control this, right? So this is the derivative square, right? Then the upper bound of BT, right? Upper bound of BT. Then we're using LP maximal inequality. So this is very important. So here we're using L2 maximal inequality. So which means we can control the super norm, right? The trajectory, right? We take the super value of the trajectory, then we take 2, right? The power 2, which can be controlled by the endpoint, right? So which can be controlled by endpoint. Which can be controlled by the endpoint. So this is the discrete version is discussed in section 4.4. Anyway, so when we do this, we can get, right, in the end, we can just get the control, right, using the variance, right? Variance is just minus 2mt. So here we not only have explicit, not only have convergence to 0, we also have convergence to 0 with a rate, right? And the rate is just the size of the larger mesh, right? So this is 2 to m. So this is the size of a larger mesh, larger mesh, or partition. So we have two partition, right? One is the final partition of another. So this is just the partition length of the larger one, right? So we have convergence to 0. So this means, right? This means L1 is a Cauchy sequence, right? So since L2 is complete, right? So IM1 will converge to I in L2, right? Right, that's what we have. IM is Cauchy sequence. And since this space is complete, right? So we have convergence in L2, right? And we just let this be the Ito integral. We just let this to be Ito integral. Okay. So this is the first part. Maybe just stop for a couple of minutes here, right, to answer questions. So any questions? Okay. 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 No questions. So we go to next. The next is exactly the same. So I probably will skip this, right? But I just go to the, go through the steps, right? So we want to show that, right? So choose 1 point, right, for between for S, right, for S. So this is S, right? S is between this time, and so here, yeah, here this should be BS something. So this should be BS, should be BS. Or C should be BS. So anyway, so let's so to do that, right? So let's introduce in ASN, ASN. So which is just the increment of the accumulated version of this part, right? So we write this as AS. So then the previous sum, right? So this sum can be written as that, right? Can written as the formal integral, right? Can written as the formal integral, right? So DAS, right? DAS is just BTIN plus 1 minus BTI square, right? So here is the sum, right? So here is just the sum, right? It's just this term, right? So what we want to do, right, is show the following, right? Show this following, right? Okay, just to show the following. So GSN, right, since by the continuous, since F prime, right, is continuous, right? So this part is easier, right? So let's just see this is GSN, right? GSN. GSN equals to F prime BS, right? So Sn, let's say Sn, right? So let's say this is Sn. So of course, right, and so if this so if this Sn converge to S, right? So this Sn converge to S. So of course, right, let's say this is Sn. So this should converge to F prime BS, right? I mean, this is trivial, right? By Brownian motion, it's continuous, right? So this typically is continuous. And F prime, right, is continuous, right? It's composition of two continuous functions, right? So this part is trivial, right? This part is trivial. So we have convergence of this part, and also we have convergence of this part, right? So that's what that, right? So DASN, so basically it's just a DBTN, so, sorry. So DS, so this part, right, is just integral. So actually I don't like this formulation, but so this is ASN, right? So we want to show is like this part. So this part before, right, we actually show this equal converge to S. This converge to S almost surely. So this is, as I said, right, it's exercise 7.1.6, right? So as n goes to infinity, right? So this up to time S, right? So we converge to S. This converge to S, right? So DASN, right? So this is kind of operator, right? So this converge to DS. I mean, this is a wedge sense, right? Its convergence is some mirror sense, right? It's a mirror, right? V convergence or mirror, right? This kind of V convergence or mirror, V convergence or mirrors, right? So then we have this type of convergence, right? So we can, right, we have convergence of functions, right? And also we can convergence, right? So you can think this DS, right, is the big mirror, right? So this is like a very big, very weird mirror, but it's a finite mirror, right? Almost surely, right? So, right, since this converge, right, ASN converge to S, and the function convert, right? So we have their integration also convert. So this is the result, right? So we use, right? We have a convergence of mirror, a convergence of finite mirror, and also the function, right? We have convergence, right? As n goes to infinity, right? Sn converge to S, and also this sequence is bounded, uniformly bounded. Then we have this convergence. Okay, so our theory, not theory, so our second convergence is just coming from here, right? Just coming from here, right? By applying, right? This is Gn, our Gn, right? And this is our mu n. But this mu n actually is a random error, right? It's a random error. So, right, so we get here is almost surely convergence. I don't want to spend more time on this because we don't have too much time. I need to discuss a little bit about SDE later, but proof is very straightforward. Proof is very straightforward. Okay. So then that's it, right? So that's it, right? So we get the previous formula. Let's just recall here, right? So we get this formula. We just get this formula, and this is just the dt. Let's do one example, right? So let's do one example here. Taking f equals to x squared, right? So taking f equals to f squared, so the derivative is 2x. The second order derivative is 2. So we can use this formula, right? First version, right? First Ito's formula. So we can use the formula, right? This is what we get, right? Bt squared, right? It's f bt, right? Minus fb0, right? Equals to this plus this. So, right, this is just the application of the formula. So that's why we get this, right? That's why you get this. Just rearranging terms. Okay, so if you have x, right? So you just integrate u, right? Du, right? Right? What do we get, right? Is u squared, right? T0, right? Just t squared, right? So right, this is too simple, right? But we can choose different one, right? Let's say it's 2, that u is a function of s, right? This is ds. Let's say u is as good as possible, deterministic, right? So what we have actually is s. square t0, right? So what we get x0 minus 0 t0. Okay? But here we have action t, right? So this is basically from the last term, right? From the Ito's correction term. Okay, this is a very easy example, right? From the exercise you did, can do this directly. We can compute this directly, right? So this is a direct proof. So the direct is very, I mean, you should know this because when you get scarcity, you can see that, right? You can find the basic idea from here. What's the direct proof, right? So let's compute BT square, right? BT square, and we using the partition we used before, right? So we partition those interval from 0 to t to two even subintervals, right? We divide those to two even subintervals, right? And this is the sum, right? So it's trivial, right? This is trivial. Then we complete the square, we complete the square. So again, two terms, right? We do two terms, right? Am I right? Okay, we decompose to three parts, right? So this is I equals to G part, right? So this is the diagonal part, and there are two off diagonal, and you can show, right? Two off diagonals are equal, right? So there are two here, right? And this is the off diagonal term. Right? For the two, for the off diagonal term, we can just sum, right? So this is our summation. So of course, as n goes to infinity, right, you have this term, right? You have this term, right? So the here, right, this is increment goes to here, right? And by our previous calculation, right, this converges to t, right? So this is really, right, exactly our exercise 7.1.6. Okay, so you can compute, right, you can show, right, bt square, right, equals to 0t bs dbs plus t, right, directly, right, from our exercise, right, our homework, right, for this particular case. But what we showed before is a general case, right? Okay. Okay, so let's just state the following theory. So I won't prove that, but you should know this, right? So this tells us, right? So as G is continuous, right? The Ito integral, right? And basically, so this theory tells us, right? Ito's integral is a martingale, gives a martingale, gives a martingale. So the theory says, right, if G is continuous, right, and have the integrability condition, so then this term is a martingale, right? This is Ito integral. Of course, right, this can be more general, right? So this can be more general, right? In general, right, G, right, GTXS, right, DB, right, you can, so XS is a stochastic process, right, which is adapted to S, right? So let's say this Fs is generating by the Brownian motion, right? Then this is a martingale term, martingale. So then this is a martingale as well, right? So for instance, if you take expectation, you get a 0, right? But we need some integrability condition like this. We need some integrability condition. Okay, so like you take the square, right? It's kind of LT1, right? And LX, right? Not XL2, but omega 2. It's kind of this. You need this type of condition, right? You integrate with time, integrate with omega, right? With the probability measure, so you get finite. Okay. So, so I don't want to check this then, but let's just skip that. So I want to just state the Ito's isometry. This is the following. So it's very easy. but I want to state this, right? So let's say xs is adapted to fs, generating by initial state, and also the branching t, motion t, and the st is less than s. So xs is the stochastic process adapted to the fs, right? So Ito's isometry says this, right? We can first compute the integral in time, then we take a square, right? Take a square, right? Take the L2 norm of respect to probability P, right? P is a probability trajectory, right? So then this equals to, okay, we first take square, right? Take square. Then later we can take the time integral. Right? So this is called Ito isometry. Ito isometry. What does this mean, right? So this basically means, right, this one. So this one. So equals to, right, equals to 0 t s, right, in norm size, right, in norm size. In norm size, right? So this is the random variable, right? This is a random variable, right? This is not this is the Ito integral, right? And this is Euro integral, right? This is the Riemann integral, right? So you take a Riemann integral, right? So here you take Ito integral, but we get the same norm, right? So in L2 sense, the norm are the same, right? In norm size are the same, right? So this is called Ito's isometry, right? So in a lot of places, right? So it's good to use this isometry formula, right? Also, right? So this is Ito integral, right? So this is a random variable, right? This is a random variable with mean 0. Right? So what we compute here, right, is actually variance of this random variable, right? And Ito's isometry tells you the way, right, how to compute the variance, right? The variance is very easy, right? You first just take the expectation, right? Take the expectation, right? By Fubini, and then you just do this, right? So this is, right, you take expectation, right, by Fubini. Right, so this tells you a way to compute the variance of martingale, right? So tells you how to compute a variance. Okay. So let's just state the following two main results. I won't want to talk about proof, right? Because we don't have time. So let's just state the second version of Ito's formula, right? The second version is, okay, now we have time dependence. Right? We have time dependence. So we have one more term. That's all, right? That's all. But the proof, right, is not as you think, right? So we need to think a little bit more, right? Because if you just think, right, Ito's formula is Taylor expansion to second order, right? So there are also the term, right? There are also cross term, right? So they should have dt, dbt, right? So if you just explain to the second order Taylor expansion, so we also have this term dt, right? We have this cross term on this term, sorry, right? So basically we need to say this term has zero contribution, right? Has zero contribution. And this term also has zero contribution. Since this is not very hard, I will skip that, right? So otherwise, I don't have time to discuss anything about stochastic differential equations. So you can just remember this formula, right? So time variable only has the first order contribution, right? So this is dbt, right? So this comes from dt. This dt comes from bt squared, right? Bt squared. So then if we write in the integral form, right? We write in the integral form, So we have that, right? So the integral in time, right? This is integral in time, right? The t term, the x term, right? So the equal term, right? Okay, then that's it, right? Right, the proof, you can find the proof in the textbook, but the idea is very easy, right? So we want to show, right, this term has zero contribution, right? Zero contribution. So this is a cross term, right? This cross term. And also dt squared term, right? So this is a dt squared term, right? So this equals to zero. The proof is very easy, right? So I will skip that. I will skip that. So yeah. Last scenes, right? Last scenes is a multi-D version, right? Multi-D version. So let's just state that, right? So say we have f, right? F is a function, right? F is a function like tx, right? So this is a function, f is from r plus times rn, right? Using rd, right? R plus times RD to R. Okay, so then, so what is Ito's formula, right? So this gives you Ito's formula. So here I have some concern. So here BS, so BS actually equals to BS1 to BSD, right? So otherwise, so here you put BT here, right? So BS is a multi-dimensional Brownian motion. So then if you if you write the integral form, so what you get, right? First term is given by the derivative in time, right? The second order term is you take derivative in space, right? So you write in a compact way, right? This is a dot product over BS, right? And also you have the Ito's correction term, right? So which is just actually, if you're writing a compact way, is 1/2 Laplacian term f BS. So here is dt, right? So this is a second order correction, right? ds, right? So if you write this in differential way, right? In the differential form, right? So then this is dft, right? bt, right? Take time derivative, right? dt, right? Take space derivative, right? This is gradient, right? This is dot product, dbt, right? So then this is Ito's correction term. So we have a Hessian term. So we have a Hessian term, and this is a cross product, right? This is cross product. So you get a matrix. Right? So this is a matrix, right? So you have U cross V, right? So what's that, right? This is just a UI with J, right? I bigger than 1, less than D, J bigger than 1, less than D, right? This product. And what is gradient f, right? This is just a Hessian, right? So you put all the derivative, second order derivative there as a matrix, right? It's a Hessian matrix. If you have two matrices with the same size, then the dot product is common product. This actually is component-wise product. So what's that, right? So this actually is just a sum ij, aij, bij. So you take the component product of A and B at the same time, then sum up, right? This is basically inner product, right? But for matrix, right? So this is the last form expressed in the textbook. But I will a little bit more. Just wait a little bit before I need to say something about stochastic differential equations. So the following is just an exercise problem. So you can look at that. So let's talk a bit by basics by stochastic differential equations. Right? So I don't write a lot, but I won't discuss that. If you're interested, you can read that. So what we have is the following theory. So there's a book. So I told you if you're interested, there's a book. So I actually copy everything from this book. It's a very good book on stochastic differential equations. So it's written by Oxendo. So I'm not sure my pronunciation right. Right? This guy may be from I don't know, Sweden, maybe Norway, maybe in Northern Europe. It's a good book on stochastic differential equations. So you can just Google, right, the name. You can just write a stochastic differential equations book, right? So maybe the very first field will give you the PDF, right? Small discussion definitely in this book, but no, it's very easy to follow, right? This book. Let me just show you a little bit. There are too many preface for different versions, right? For this part, basically we already know, but yeah. So this is the basic part, right? This part you definitely know now. This part you know. This part you basically know, right? This part you basically know already, right? The Ito formula martingale representation. This is what we want to say a little bit, right? So then when you know SDE, right, you can study other things, right? You can study like diffusion process, right? Diffusion. Right? You can study, right, some relation with PDE, right? So angular equation, right, forward equation, and you can apply this to study boundary value problem, right? Initial value problem, right? Something like that, right? So like optimal stopping, right, for stock market or something, like optimal control problem, stochastic control, right? The Hamilton-Jacobi-Bellman equation, right? This is not a very hard book, but you are interested in stochastic differential equations. This is a very good introductory book. Okay. So what is SDE, right? So what is SDE, right? So usually we just write in the following way, right? So this is drift term, right? This is a drift term. Then this is a dispersion or diffusion term, right? This is a diffusion term. And theta, right, sigma, right, is the coefficient before this Brownian motion, right, before this Brownian motion, right, dxt. So what does this really mean, right? What does this SD really mean, right? So as we know, right, so when we write a SDE, right, so we really means it's a integral equation, right? So here, what it means is the following, right? What we really mean is this. Right. All right, now we already know, right, this is just the Ito integral, right? This is just the Ito integral, right? We know the meaning of the Ito integral part, right? We know the meaning of that. Right, this is just the Euler integral, right? And we want to solve, like, this equation, right? SDE, stochastic differential equation. But how to solve that, right? So I feel most equation you cannot solve explicitly, but only solve using approximation, using numerical methods. So you can solve some equation by hand, right? So I will give you, maybe I give you an exercise, and you can take, actually I compute this here, right? The gross model, right? You can compute if you are interested, right? This is just a model I told you in last lecture, right? In last lecture, so we study one example called theta bt, right, minus 1 theta square t. So this is a martingale. We proved this is a martingale, and you can, so you can get this. You can write this as SDE, right? So we can write this as T, right? You can show dST over ST actually equals to theta BT. you can write this as a stochastic equation, right? dst equals to theta st dbt, right? So st is really a martingale, right? You can check this is a martingale, right? Using, because you can write this as a stochastic, as Ito's integral. Right? You can check it using the following way as well. So I do some computation here, and if you look at the computation in the end of the last lecture, because some student asked me that question, so I write a little bit in the end of last lecture notes. There are also discussion there, but most equation you cannot solve that, right? So this equation you can really solve that, right? Let's say for this equation you can solve that, right? So if we know ST, right, solve the following stochastic differential equations, right, we can solve this, right? So the solution is just what we write, right? The solution is just ST equals to exponential theta t minus half theta t t, right? So of course the initial time, right, right? So we should write it in the following way. So this is a solution. But most SDE, right, stochastic differential equation has no explicit or analytic way of solutions. So basically what we only know is this theory, right? There are recent development of there are some discussion on weak solutions, right, which is not a solution we discussed here. But except that, right? Except the recent like research progress or some development of weak solutions, right? This is the only result we have, right, for stochastic differential equations on the existence and the uniqueness. So what do we have right here, right? So we have, right, as long as the coefficient does not grow too fast, right? So linear growth, right? So it's linear growth. So we have linear growth, also Lipschitz condition, right? So Lipschitz condition in X, right? And this is uniform in X. So this actually is called T infinity Wx infinity. So which means it's Lipschitz in X, and this is true for all time, right? So this is Lipschitz in X, but uniform in time, right? As long as you have these two properties, right, so given initial time, given initial state z, right, so z is a random variable as well. So z is the initial random variable, right, which is the initial for x0, right? So x0 is independent of the Brownian motion, right, the motion. So then we can construct not explicit, we can construct solutions which is continuous, which is time continuous, and depth filtration ftz. So this filtration z, right, is generated by the initial state and also the bs s less than t. Okay. So then we can do everything, right? And we can show, right, this is bounded up to any finite time z, finite time t, right, is so this is x, right, actually is in LT1 L. So this is integrable in time, and also is L2 in omega. Okay, so in X. So this is almost the only result on the existence and the uniqueness for stochastic differential equation. And the solution we have, we called the solution strong solution. We call the solution constructed in the proof called strong solution. And we have uniqueness, right? We have uniqueness, right? This is the meaning of uniqueness. Sometimes we call pathwise uniqueness. So this is pathwise, right? As you have another solution, so then you can show almost everywhere, well, almost every omega, for almost every omega, right? They are they're the same, right? It's pathwise unique. So it's called a strong solution because there's a weak notion of solution, right? It's called weak solution for the SDE, right? But this weak solution is quite different to the weak solution in PD, right? So the strong solution, right, which construct here also is not a strong solution for PE. It's different names. Okay. I think I basically talk. Yeah, basically I've just stopped here. If you have questions, we can on, but otherwise, right, this is some discussion on weak solution. But I don't want to say more about them because it will get you more confused, right? So basically for weak solution, right, we only given like coefficient, right? For these two coefficient, we construct Brownian motion, right? Construct Brownian motion and filtration. So then, so we solve let me solve this equation, right? So so actually what we do is not just to solve the equation, right? Actually find xt and also find the Brownian motion. But the previous construction is, so this bt, right, this Brownian motion actually is given. Right? So we given a Brownian motion, right? We given filtration ftz, right? So z is initial data, right? Given initial data and given Brownian motion, and given b, the coefficient, given theta, the diffusion coefficient, and we can solve this equation. So that's different, right? So I mean, for your current purpose, is to just know this result, right? The existence and the uniqueness result for stochastic differential equation with coefficient that does not grow too fast and also is Lipschitz, right? So maybe a few words about proof, right? So we definitely cannot prove that, but the proof is so it's called Picard iteration. So this is the same, right, as in ODE theory, right, in ordinary differential equations. In ordinary differential equations, so what we have here is called Cauchy-Lipschitz theory. So the proof is the same, right? Not exactly the same. It's the spirit is the same. Basically, you starting from like a constant function, right? You iterate that. Right? You construct from x0, you construct x1, x2, xt, right? So xn, right? Then you are convergent, you have a Cauchy sequence, right? So in the end, you can construct the solution, right? Basically using like fixed point things, right? Fixed point argument, right? Using, this is called Picard iteration. So if you study ordinary differential equation before, right, this is called a Cauchy-Lipschitz theory, right? On same conditions, right, not grows too fast and have Lipschitz condition, then you can have existence and uniqueness for the differential equations. But of course, the existence part, you don't need to use this on assumptions, right? So that's, yeah. I will just stop here. I will contact you separately. I want to send an announcement to all of you, right? So I will contact you by email. So if I want to talk to you a little bit, but otherwise, that's all for this semester. If you have questions, let's answer your question first. No questions? Okay. So definitely this even we are a little bit lost in the last part, but this actually are very important materials, right? So if you so recently, right? So people find a lot of applications of stochastic analysis. I mean, even in data science, right? It's a very important subject, right? I mean, traditionally, it's a very important subject. There are several people won Nobel Prize, right, working on this. Okay, this field, right? Not I mean, this is just a very basic thing. Yeah, so that's all for this semester, right? So if you have a question, you can ask. I will contact you separately, right, via email if I want to interview you, talk to you, right? Not the interview, right? A little bit. So, but otherwise, that's all for this semester. There's no homework for this for today's material. And yeah, enjoy yourself. Yeah, I will stop recording.